Yeah, so welcome everyone to the NPTEL course on the Introduction to Polymer Physics. And the course instructor for this course is Professor Amit Kumar, Department of Chemical Engineering, IIT Guwahati. And I am the teaching assistant of this course. My name is Shikha Sharma, and I am a research scholar in the Department of Chemical Engineering, IIT Guwahati. And today, this is a live interaction session for week 5, and the topic is branching, network formation and generation of the polymers. Uh, so the topics which we have covered in the last class were we, det- we covered these following topics, like we find the determination of polymer molar mass by light scattering method. So we discussed the uh, polymer molar mass by the light scattering method. In that we discussed about the static light scattering, the relay equations and the excess relay ratio. After that we discussed about the light scattering by dilute solutions. Then we discussed about the Zim plot, and then we discussed about the frictional properties and the viscometry. In that we discussed about the intrinsic viscosity, and then we discussed about the MHS equation, which is Markov-Hen's equation, and then we discussed the final topic was size exclusion chromatography, which is also known as gel permeation chromatography. So we solved some of the problems based on the GPC. So in the today, uh, like in the today's class, what we will be covering? We will be covering the branching, the hyperbranched polymers, the branching, and what will happen when the cross-linking will proceed, like the network will form, so network formation, and the gelation in the polymers, how it happens. And then we will discuss about gelation and the swelling of network polymers. So in this live interaction class, we will try to solve some of the problems, and we will also try to discuss some of the concepts regarding the branching, network formation, and gelation. And I hope you have already gone through the three lecture videos provided on the NPTEL platform. So, and also when we will solve these problems, like when we solve the problems or we will discuss the today's problems, if you find some queries or you have some queries, you please feel free to ask. Okay, so can we start with the today's session? So let's begin with the problem number 1. So it says that, sorry, uh, so, so let's discuss problem number 1 of today's class, which is polymerization of ARB F minus 1 type of monomers, where A, here A is and B is, they are mutually reactive functional group. So A is a functional group. R means that it is reactive with the B functional group. So we are saying it ARB F subscript F minus 1, a type of the monomers. So when we do the polymerization of such monomers, then what will, and if the functionality is equals to 1, here A and B, they are mutually reactive, but A does not react with A and B does not react with B. So these type of the monomers in which A is reactive with B, but A and A is not reactive and B is also not reactive. So this, and when the functionality is equals to 3, then we get which type of the polymers? We get linear polymers, we get hyper branched polymers, C is dendrimers we get, or the network polymers we get. So, uh, anyone will like to answer this question? So, what happens is this answer is hyper branched polymer. So, what happens is the functionality, like when the functionality, the F value, this F value, if it equals to 2, the functionality of a monomer equals to 2, then it means that it is a linear polymer. So this answer cannot be correct because F equals to 3 is here given in the question. Then second is hyperbranched, which is our correct answer. So in hyperbranched dendrimers and network polymers, the functionality is equals to 3. In these three cases, functionality should equals to 3 or greater than 2. So, why dendrimer and network polymers are not the correct options? Because in the dendrimers, the polymerization of ARBF-1 type of monomers are there, but plus RBN monomers, this type of monomers like A and B, which are mutually reactive functional groups. So, ARBF-1 type of monomers and RBN type of monomers when it is there, and uh, in this A and B these are mutually reactive functional groups, and third condition is the F should be greater than 2. So in all these three cases, F, B, C, and D, which is hyperbranched polymers, dendrimers, and the network polymers, the functionality will be always equal is greater than 2 or more than 2, or like here it's given 3. So any of these can be correct, but as we discussed, dendrimers, they are the polymers, like they in the dendrimers, the monomers, they are these two type of monomers should be there, but here only one ARB subscript F minus 1 type of monomer is there. So dendrimers cannot be there. We cannot obtain dendrimers. In network polymers, what happen is there is a polymerization of A, sorry, RA2, RB3 and RB2 type of monomers. So where A and B are mutually reactive functional groups and A can only react with B and vice versa. So in this, when these three monomers will be there, the polymerization of these three monomers will be there, then we get the network polymers. So this cannot be correct. Only hyperbranched polymers can be correct in this case. So you understood the different cases, like when the functionality is equals to 2, then we get the linear polymers. When the functionality will be more than 2. So which is in this case F equals to 3, we can get hyperbranched or dendrimers or network polymers. But in the dendrimers, we have ARB F minus 1 plus RBN. This type of monomer should be there for the polymerization. But in the network and in the network polymer, RA2 plus RB3 plus RB2 types of the monomer should be there for the polymerization. So these two options also cannot be correct. So option B can only be correct, which is hyperbranched polymers, which is having A, R, B, F minus 1 type of the monomers for their polymerization. Okay, can we move forward? Yeah, so next question is consider the polymerization of ARB F minus 1 type of monomers to produce hyperbranched polymers where A and B are mutually reactive functional groups, but A does not react with A and B does not react with B, and F equals to 4. So here in the question, functionality is given as 4, and is saying that A, R, B, F minus 1 type of the monomers is there. So it is a hyper branched type of system, right? Now it is saying the number fraction of n monomers, which is the monomers, n monomers is represented by n to, uh, in the function of probability. P means is the probability that a group has reacted. So P is the probability. So it is saying that the number fraction of the n monomers. So number fraction is given as the small n subscript n monomers to in the function of the probability of the group, the reacted group. Okay, and then it is saying that the first and second movements of this number fraction of n monomers is given by these two formulas. The summation from n1 to infinity, where n is the number, this n capital N is the number of the n number of the monomers, right? This small n in the function of p is the volume fraction, right? Is equals to 1 upon 1 minus p multiply f minus 1. Small f is the functionality, which is uh, the functionality. And then it is saying this first term is denoting the first movement, and the second term is this denoting, the square term is denoting the second movement. So it is saying the summation from capital N from 1 to infinity. So our uh, monomers can be like, they can be from 1 to infinity, and n square, capital N square multiplied by small n function of p equals to 1 minus p square multiply f minus 1 whole divided by 1 minus p multiplied by f minus 1 and whole to the power cube respectively. So this is our second movement. Now there are two sub questions, and A is saying, like, asking to calculate weight average degree of polymerization at an extent of reaction 0.3, and second is saying to calculate PDI, which is nothing but polydispersity index at the extent of the reaction 0.3. So you understood the question, what it is saying? It is saying to calculate the PDI and weight average degree of polymerization when the extent of the reaction is given. Yeah, so I am moving forward, right? So let's solve this question. In this, we need to, in the first part, we need to calculate weight average degree of polymerization. So how we calculate weight average degree of polymerization? It is equals to the second movement divided by the first movement. So second movement, this formula is already given to us, which is in the square format, right? So we can write the second movement, this one, from this, we can put this value, right? And divide by the first movement. First movement is this, right? This whole, and then we can put it in the denominator. When we put this value 1 minus p square, which is 1 minus p square multiplied by f minus 1 to the to divide by 1 minus p f minus 1 to the power cube. So this is the second movement value we are putting directly divide by the first movement value, which is 1 upon 1 minus p multiply by f minus 1. So we can get here we can cancel this one and here 2, right? So 1 minus p square f minus 1 divided by 1 minus p f minus 1 whole to the power 2, which we can in this we can put the value p is the extent of the reaction, which is given in the question as 0.3. So 1 minus 0.3 square, and f, which is the functionality, is given in the question as 4. So multiply by f minus 1, which is 4 minus 1, divide by 1 minus p, which is 0.3, and then multiply by f minus 1, which is 4 minus 1 whole to the power 2 square, sorry. So when we calculate, we'll get it here 3, right? Multiplying by zero point 0.3 square, which is 0.09, and we can get from this 0.27. 1 minus 0.27 is 0.73 in the numerator, and 1 minus 0.3, and here it's 4 minus 1 3. So 4 minus 1 is 3, multiply by 0.3, which is 0.9. 1 minus 0.9 is 0.1, and its square is 0.01. We get it denominator. So when we divide, we will get our weight average degree of polymerization is equals to 73. So first part, is it clear, everyone?
Yes.
Okay. So next is calculating polydispersity index in this reaction. So we already know from our previous lectures and previous discussions that polydispersity index is nothing but the weight average degree of polymerization the uh, weight average degree of polymerization divided by number average degree of polymerization, right? So we get like we can divide from these two values like NW, which is the weight average molecular weight, divided by the number average molecular weight Mn, equals to the weight average degree of polymerization divided by number average degree of polymerization. So polydispersity index formula we already know, right? Is equals to, so we know that in the denominator it's weight average degree of polymerization. So what this is, we already discussed in our previous slide that it is nothing but second movement divided by the first movement, and we get 1 minus p square multiply by f minus 1 here, sorry, from this whole equation we calculated already what is weight average degree of polymerization in terms of the movements value. So second movement divided by first movement. So we got this equation, right? So in this we need to just put the weight average degree of polymerization value, which is 1 minus p square multiply by f minus 1 divided by 1 minus p f minus 1 multiply में then whole to the power 2, which is square, divide by the number average degree of polymerization, which is nothing but what it is. It is given below that it is number of monomers present initially divided by number of the molecules present in the reaction mixture. So it is nothing but it is equals to 1 divided by 1 minus P multiply F minus 1, right? So this is also discussed in the lecture slides also, that the number average degree of polymerization formula is 1 upon 1 minus P multiplied by F minus 1. So it is equals to this whole term, the PDI term will be coming to, since this will cancel out with this. So here we will get 1 power. So 1 minus P square multiplied by F minus 1, and in the denominator the square power will come to 1. So 1 minus P multiplied by F minus 1, and then we can just put the value, which is P equals to 0.3 given in the question here, that the extent of the reaction P is nothing but it is equals to extent of the reaction. So 1 minus P square, which is 1 minus 0.3 square, and then multiply with the F minus 1, which is F is already given in the question as 4, which is here, right? So 4 minus 1 divided by 1 minus P, which is 0.3 multiplied by F minus 1, which is 4 minus 1, right? Then again, we can just calculate and simplify and calculate and get the PDI value. So 4 minus 1 is nothing but it is 3. Here it is 0.09. So 0.09 multiplied by 3 is 0.27, minus 1 is 0.73, right? And in the denominator it is, here 4 minus 1 is 3, and then multiply by zero point 0.3, which is 0.9. 1 minus 1 minus 0.9 is nothing but 0.1, right? Then we can get here as 7.3 our PDI, which is polydispersity index value. So are you solving with me?
Yes, yes.
So let's move to the next question, which is the ratio of the root mean square radius of gyration of a randomly branched polymer having 2000 monomeric unit to that having 500 monomeric unit is. So we need to calculate the ratio of the root mean square radius of gyration of a randomly branched polymer whose monomeric units, which is capital N value, is given as 2000 and 500 monomeric units. So we need to calculate the ratio of the root mean square radius of gyration. So what is the relation between radius root mean square radius of gyration and n? So what is the relation? Okay, so you got the answer as 1.41. Okay, so let's see this the solution part. So the ratio of the root mean square radius of gyration of a randomly branched polymer having 200 monomeric units to that having 500 monomeric units is, the relation is this, which the relation which we were discussing in the previous slide, that radius, what is the relation between the radius of gyration. So the radius of gyration, square radius of gyration, directly proportional to the square root of the number of the monomeric units, right? So if we take the square root both sides, which, because we need to calculate the root mean square radius of gyration. So we can take square root both the side and we can get this formula, the relation that uh, the root mean square radius of gyration is directly proportional to n to the power 1 upon 4. So it is as it is directly proportional, we can uh, we can put this formula as root mean square radius of gyration for the second one, which is like in the second case divided by in the first case is equals to number of the monomers in the second case to the power 1 upon 4 divided by number of the monomers in the first case, uh, and its power is 1 upon 4. So in the second case we are taking 2000 as a second case, right? Because our monomeric units were initially 500 and then it was 2000 monomeric units. So 2000 to the power 1 upon 4 divided by 500 to the power 1 upon 4 is equals to 2000 to the power 1 upon 4 is nothing but 6.687, and in the denominator it's 500 to the power 1 upon 4, which is nothing but the monomeric units, 500 monomeric units. So 4.729, when we divide we get 1.414 as our answer, which is what you have also calculated, right? So everyone understand or the following the problem?
Yes.
So yeah, you got the correct answer. So next move to the next question, which is a sample of natural rubber, which is cis 1,4 polyisoprene, is vulcanized such that one of every 240 chain carbon atoms is cross-linked. The formula unit of the isoprene monomer is C5H8. The molecular weight is equals to 68 gram per mole. So the average molecular weight we need to calculate between crosslinks is, so we have a sample of natural rubber and it is vulcanized, which is it is having the sulfur linkages. Also, it is saying that in the that every 240 chain carbon atom is cross-linked, right? So, and it's the monomer, which is the isoprene, its molecular weight is also given as 68. So, it is asking average molecular weight between cross-links. So, how we can calculate this? How we can approach this first? Number of isoprene units we need to calculate. Hmm. Then we can calculate molecular weight. Yeah, true, true. So we know that that in the polyisoprene, this is polyisoprene, which is the natural rubber. It looks like this, right? So in this carbon is there, then this carbon is there, this carbon is there, and this carbon is there. So in like we have a 4 carbon in the linkage, right? So every 240 chain carbon atom is in cross link. So in the chain, the carbon atom is basically there in the forming cross link. And in the monomer, we are having 4 carbon atoms. So number of the monomers between, we will calculate first number of monomers. What is the number of monomers between two cross links? So there are two crosslink like this, two crosslinks are there, and then uh, in that we need to calculate the number of monomers, which is nothing but 240 divided by 4, because we are having this like in like after every 240 carbon chains there is this cross linking, right? So in the 240 chain we have this four carbon atoms which are in the cross, which are taking part in the cross linking, right? So like this, in this structure we can see that there are total five carbon atoms there in the structure of the like the structure of the isoprene, but only four carbon atom will going to participate in the cross linking. This carbon atoms, this is not taking part in the linking, right?
Okay, okay.
So we are taking here, we are dividing it by 4, not by 5, because this carbon atom is not taking part in the cross linking. Only these four will take part. This four. So from this we can understand, like if there are four carbon atom in one cross link, right? So how is the number of the monomer in the 240 chain? We can just simply divide and we get 60 monomers we are having in short, right? Then molecular weight, one isoprene molecular weight is 68. So we can multiply 68 into 60, which is 4080 average molecular weight between these cross links, right? So you understood why we took 4, not the 5?
Yeah, yeah, I understood.
Yeah, so that's why we are taking, because it is not in the cross linking, because we need to understand the structure in deeper, how the cross linking will be there in the polymer, so that we can understand that uh, only four carbon atoms will going to be there in the cross link. So we are dividing it by 4. Okay, so let's move to the, and so we got the answer as average molecular weight between cross link is equals to 4080. So next question is, now we will going to discuss about, before we were discussing about mainly the hyper branched system. Now we are further discussing about the dendrimers. Okay, so let's discuss some of the concepts of the dendrimers, which is what is the typical growth pattern of a dendrimer: linear, exponential, random, cyclic. So anyone? Yeah, true, true. Exponential, correct answer. So we know that dendrimer is actually a highly branched structure. Like we can see on the right side, this is a highly branched structure, and we can see it is a tree-like structure or a globular macromolecule in the shape of the micelles. We also say where uh, where this inner or the innermost part, which is also known as the core, and it is also known as the starting point of the branching, from where the branching, all these branching will start. It is known as the core. And then after this there are layers of these branching units, which are known as the generation, which is represented as G. So here this is core, this is here, this is branching, right? From this is branching. So till here, till first it is generation 1, then it is the this is the second, this is the generation 2. So these are the different layers of the branching which we known as the generation. Like this, we'll have we will have several generations, and then there is this outermost layer of the dendrimer, which is known as the periphery, the outermost layer, right? And here, uh, this is the outermost. So this, like this, there will be one core from where the branchings will start, and it will proceed through the generation, and at the end there will be the outer periphery. This is the structure of a dendrimer. So dendrimers are also known as star bursts, we know, cascade, we know, hyperbranched, cauliflower, and and arboreals. Why these different names? Because it is looking like a tree or the globular macromolecular structure. So these dendrimers are also named or known as these different names. Also, as we know that in the hyperbranched dendrimers and the networks, there is the functionality which is F is equals to F equals to 3, right? Or F is greater than equals to 3, right? So, uh, like this, our dendrimer structure looks like, and it will from functionality 3 here and the core, it will grow, right? And at the periphery, there will be having the function where various functional groups at the surface. We will have like here we started with one, and here if we see there is this increasing the functionality, because we will have more branches, like the branching will also increase as we move from the core to the periphery. Also there is a covalent bonding form for the branching in the dendrimers. So it is associated with mostly the covalent bonds. And in the dendrimers, this is the core, right? And here we are proceeding with the branching, but this area is the cavity. So dendrimer is highly branched with cavities at each generation. So at each generation there will be some cavity, some empty space will be there, because if this generation is proceeding, this space is nothing but it is empty, right? So it is a cavity, and these dendrimers, they are basically very useful, and they are very advantages for highly branched structure of dendrimers, because it is having ability to form or to encapsulate the guest molecule, because at the core we have some molecule and we can have the branching, so it can encapsulate any guest molecule. So this is our, just we are revising the structure of the dendrimer and the basic concepts of the dendrimers. And here from the core to the end, or the to the periphery, it will grow exponentially, because at initial there will be just functionality 3, and there will be just one core will one like this one core is there, and three functionality is there, three bonds will form, right? From this it will further form more bonds, right? And from this it will further form more bonds as we move towards the periphery or the outer surface. It will it is growing, like increasing, right, exponentially. So the exponential is the correct answer. It is not going like it is not increasing randomly. It is exponentially. It is growing. Next question is the molecular dimension of dendrimers lie in the range of A 1 to 100 nanometers, B 100 to 500 nanometers, C 600 to 800 nanometers, D 800 to 1000 nanometers. So anybody?
No idea.
So it is option number A, which is 1 to 100 nanometers. So this dendrimers is in the nanometers range, right? We cannot see it. So the molecular dimension of the dendrimer lies in the range of 1 to 100 nanometers. So dendrimers can be used as a solubilizing agent. So it is also using as a application is one is encapsulating, second is as a solubilizing agent because the size is very small. There is a limit to the size of the dendrimer segments because of why there is a limit because steric conjunction is there and the space filling is there as we discussed that as we move from the core to the outer periphery there will be more of the branching and more molecules will be there, more branches will be there. So at higher levels, higher generations, there will be the space filling and steric conjunction will be there. So the size will limit, right? The space filling is there that occurs because of the growth of the dendrimer. As we grow the dendrimer, the branching will be more and space will be less. So there will be steric conjunction, right? Due to which, because of that, it has not been possible to prepare more than 5 generations. So maximum, like in most of the cases, we can just go till 5 generation because of the less space. Uh, so we have the 5 generations dendrimers. After that, we does not get. Therefore, either the reaction like therefore either the reaction to a higher generation stops completely. So we will not go in the more generations because at that thus because of the less space the reaction will stop or the outermost shell develops imperfection or in the outermost cells imperfections will be there because there is no space to like enough space to grow as a dendrimer. So we have to stop the if we want to have a perfect dendrimer we should stop it till 5 generation, right? And at till the 5 generation the size will be around 1 to 100 nanometer. So it is basically a theoretical question we are discussing, the concept based questions, so that we can refresh our concepts, right? So any doubt?
No, no.
So let's move to the next question. Consider a dendrimer formed by the polymerization of ARB F-1 plus BN type of monomer, which is nothing but it is used in the dendrimer, right? This type of monomer, where F and N equals to 3, which is functionality, and monomers equals to 3, and the number of the monomers it is asking in the fifth generation. So we need to calculate how many monomers are there in the fifth generation. So let's calculate. As we know that the number of monomers increase exponentially. So in the fifth generation, it will be n f minus 1 to the power the generation minus 1 g minus 1, right? So n is nothing but number of monomers which is equals to 3 given in the question. multiply by f minus 1. F is nothing but 3, which is given in the question. So, and g minus 1 to the power g minus 1, it is generation minus 1 is, generation is fifth. We need to calculate number of the monomers in the fifth generation. So, it is equals to n equals to 3 multiplied by 3 minus 1, which is the functionality minus 1 to the power 5 minus 1, which is generation minus 1, which is the 4. So, we can get here as 2, 2 to the power 4 multiplied by 3, 3 multiplied by 2 to the power 4, which is nothing but 48. So, you understood? So, let's move to
Yes.
the next question. Yeah, so we are moving to the next question. As dendrimers have high surface functionality, so they tends to be dash soluble than linear polymers, more less equally very less. So we know that the functionality it increases when we go from, like in the dendrimers, we know the dendrimers structure, right? From the core to when we go to towards the outer periphery, what will happen? The more branching will be there, right? And more functional groups will be there. So mostly the answer will be
A.
A, more, right? You're correct. Why? Because we have just now discussed that as we move from the core to the periphery in a dendrimer, right? Which means moving from the lower to the higher generation, then branching will increase, so the density also increase, right? The branching increases and density also increases. Therefore, at surface, high density of the functional group is present. So, surface functionality or the reactivity is higher, and also higher solubility at the surface, because there will be more like reactive groups will be there, which can easily react with the solvent and will be more, like form the more solubility. So higher will be the solubility. Next is due to lack of chain entanglement, dendrimers usually have low solubility, viscosity, boiling point, or the conductivity, because in the dendrimers there is lesser chain entanglements, because they are not entangled, they full form uh, like deficiency of entangled chains will be there. There is like more free chains will be there, right? Because there is a branching in that in the dendrimers. So what will happen? Low. So the which property will be low? So anyone? So we are discussing it. The answer is C, which is viscosity. Due to the lack or the deficiency in the entangled chains, the dendrimers will have the low viscosity, because when the dendrimers, they are not entangled or they are not in the entangled form, that means they are uh, they can have a like non-crystalline structure, and because of that because why these are there, because there is a high branching in the dendrimer's structure, so that's why they have the poor mechanical properties also. And because the dendrimer polymers, they have the low viscosity, they are used as the viscosity control agents also. Third application is uh, rheology control agents, and the other two applications were, they can be used as encapsulating agents and also the solubilizing agents. right? Why we have the low viscosity? Because there are high number of the branches, right?
Right.
So let's move to the next question. Consider a dendrimer formed by the polymerization of ARBF minus 1 plus BN type of monomer, which is nothing but it is the dendrimer's form, right? Where F and N equals to 4. The ratio of the number of the monomers in the ninth generation to that of the rest of the dendrimers is, we need to calculate the ratio of the monomers in the 19th generation to that of the rest of the dendrimer, which is up to 18th generation. We need to calculate, right? So how we can calculate? So let's solve this question. Number of the monomers in the 19th generation is equals to this formula, right? In the, sorry, uh, I am very sorry that it is ninth generation, not the 19th, right? So we need to calculate in the ninth generation, right? So number of the monomers in the ninth generation is equals to n, which is the number of the monomer multiplied by f minus 1, which is the functionality minus 1 to the power g minus 1, which is the generation minus 1 is 9 minus 1, right? Which is nothing but 8. Here we can write it as 8, and n is equals to, it's given f equals to n equals to 4. So n, which is the number of monomer, is 4 multiplied by f minus 1, which is 4 minus 1 to the power 9 minus 1, which is 8. So this is 3, 4 minus 1 is 3, multiply 3 to the power 8 multiply by 4. So it is nothing but 26244. Now we need to take the ratio of the monomers in the ninth generation to the up to the eighth generation, right? So up to eighth generation, how we can calculate is 1 plus, this is the formula, 1 plus, when we need to calculate the rest of the generations, how we can calculate 1 plus n, which is nothing but the number of monomers multiplied by f minus 1, which is the functionality minus 1 to the power g minus 1, which is generation minus 1, which is to the power generation, then whole is minus 1, and in the denominator it is divided by f minus 2, which is functionality minus 2, is equals to 1 plus n, which is number of monomers as 4, and then multiply by f minus 1, which is functionality minus 1, is equals to 4 minus 1, and to the power g, which is 8 till 8th generation we need to calculate. So 8, and then minus 1 divided by f minus 2, which is functionality minus 2, equals to 4 minus 2. So 1 plus 4, here denominator 4 minus 1 is 4 minus 2 is 2. 4 in the numerator it's 4 minus 1 to the power 8. So here 3 to the power 8 minus 1. So when we calculate 1 plus 4 and then multiply by 3 to the power 8 minus 1, denominator is divided by 2, is equals to 13,121. So we can take, now we have the number of the monomers in the ninth generation and number of the monomers in the eighth generation. So we can just take the ratio. So ratio of number of monomers in the ninth generation to the rest dendrimers will be this 26,244 divided by 13,121, and we can get around 2. The ratio is around 2. So are you getting the same answer? So let's move to the next question. What happens to the molecular weight of a polymer as cross-linking increases? So it decreases, it remains constant, it increases indefinitely, molecular weight becomes infinite at the gel point. So now it is saying that if the molecular weight of a polymer, like what happens to that molecular weight of a polymer when the cross-linking increases, how the cross-linking affects molecular weight of the polymer. So,
Yes, let me guess. I
so
think it's D.
yeah, it's correct. The answer D is correct. As you said, molecular weight becomes infinite at the gel point. So what happens is the cross-linking of the polymer chain, when there will be more cross-linking, there will be the formation of the network polymers or the gels will form, right? This gel will be formed. At the gel point, there is a this soul gel system occurs in which there is some part which is the gel or the gelled portion in the reaction mixture, and it is a insoluble polymer fraction, and the other fraction is the soluble portion which is the soluble portion in the or the soluble polymer fraction. So there is what happens at gel point, there is two system which is a sol and a gel. Sol is a soluble part and gel is a solid or the insoluble um, polymer fraction. In the insoluble fraction, which is the gel, there will be more cross-linking between the polymeric chains and leading to the formation of essentially a single macromolecule, macroscopic molecule, right? So when there is a sol kind of system will be there, and in that more cross-linking will be there, then it will go towards the gel-like structure, and at there is a point which is known as the gel point where the sol gel system will be there. In that some portion is in the gel form, which is the insoluble polymer fraction, and some will be in the soluble form. And after that gel point, which is mentioned like in this, that after the gel point there will be more like gel will be there. So infinite gel system will form, which has the infinite molecules and the finite branched molecules. Like there will be like before there will be more kind of sol system. At the gel point there will be sol gel system, and above the gel point there will be complete gel will form, which will have the infinite molecules and the finite branch molecules, and it will have more molecular weight. So at it is saying what happened to the molecular weight of a polymer as cross-linking increases. So as the cross-linking increases, the molecular weight it become infinite, because infinite at the gel point. So at the gel point and the above gel point, what will going to happen? There will be more of the branching, and as the branching will increase, there will be formation of the complete gel structure, and which is having very high or the infinite molecular weight, because there will be infinite branching. So there will be like infinite number of the molecules, they will be associated in a complete like gel. So there will be many branches, like we discussed already, that as we increase the cross linking, so initially there will be some molecules in the branches, right? Then as we increase the branches, the more molecules will participate, and further there will be like after so many cross linking, or at the gel point or after the gel point, there will be the infinite number of the molecules which will be associated in the branching. So the infinite molecular weight, because infinite molecules are there. Like we can understand there is one system we can see when we put gelatin in the water, we can get some elastic kind of the solid which is known as the gel, and it is having infinite molecules. And if we measure the weight, the molecular weight will also become infinite because there are infinite molecules in it, right? So let's discuss the next concept in the gelation, which is which of the following does not result in chemical gelation. So A, hydrogen bonding, addition polymerization, condensation polymerization, vulcanization. So there are two type of gelation. We know that one is the physical and one is the chemical. In the physical gelation, there are formation of the physical bonds, while in the
A.
chemical gelation, yeah, while in the chemical gelation, there are formation of the chemical bonds, right? So you are saying which one of the following does not result in chemical gelation. So you are saying A is the answer, right? So let's see. You're
Yes.
correct. Yeah, you're correct. It is hydrogen bonding because in the chemical gelation there are the formation of the chemical bonds like the vulcanization, or there is the formation of the covalent bonds or like that. But hydrogen bond is a physical gelation, right? So it is incorrect. Next is how does the viscosity vary with the onset of the gelation of reaction mixture? Increases, decreases, remains constant, none of the above. How does the viscosity effect when there is a gelation in the reaction mixture? So what will happen? Anyone?
A.
So you are saying A is the correct answer. So yes, A is correct answer because with the onset of the gelation, we will have some medium kind of viscosity, but that will dramatically or that will rapidly that will be increased when there is a formation of the gel in, or there will be gelation in the reaction mixture. Like this, we can see in the graph also, where x in the y-axis the viscosity is there, and in the x-axis there is the time of the reaction. So there is a variation in the viscosity like this is the variation in the viscosity, right? And here if we see, initially it is slowly increasing, but which is having some, like the solution will have some kind of viscosity, but when the gel will form or the gel point will be there is a rapid increase or the dramatic increase in the viscosity because the gel has formed, right? So, and in we can say, like in the second point, it is said that gel point is defined as the point in the reaction where the system loses the fluidity, where our system loses the fluidity and the viscosity becomes so large that an air bubble cannot rise through it. So, at the gel point, our system will not be a liquid anymore. It will lose its fluidity and the viscosity. It will like it will more be in a gel-like form. So its viscosity will increase and it will become a elastic solid-like structure. Also, we can see that the degree of polymerization, number average degree of polymerization is also in, like it increases when the gel, like at the gel point it is very high, but it is slowly it is increasing. No, it is not having any dramatic effect or the drastic effect is not there, but it increases as the time of the reaction increases. Also, we can see the extent of the reaction, which is P. In P, it also increases as the time of the reaction it increases. So when there is a more conversion, when the extent of the reaction also, this as per the time it increases. Like initially it is very high, matlab at the initial time, the initial when the reaction initiates, the value of P is very high, so the extent of the reaction is very high. But when the reaction becomes at like it's on the more time, or when the reaction is taking place for long, then it is slowly becoming constant, right? So let's move to the next question. Can the following alkyl recipe be reacted to complete conversion of the limiting reactant without gelation? So these are our these three. So it is saying that can the following alkyl recipe be reacted to complete conversion of the limiting reactant without the gelation? So we have these three, this glycerol we are having, pentaerythrol we are having, and phthalic anhydride we are having, and these are different moles of them. These are given, right? So first, what is the limiting reactant is there? So is the reaction will take place uh, without the gelation or not? We need to see this, right? So let's approach this question. So we are having phthalic anhydride, which is having 2 moles, and it is having the functionality as 2. So we can calculate the equivalence. So equivalent is nothing but moles into functionality, which is moles is 2, which is given in the question, and we know that the phthalic anhydride is having 2 functionality. So we can multiply and we can get the equivalence. So 2 into 2 equals to 4. The glycerol, we know that its moles is 0.3. So functionality is 3 in the glycerol. So 0.3 into 3 equals to 0.9 equivalents in the glycerol, and erythritol is having 0.6 moles and functionality is having 4. So equivalent will be 0.6 into 4 equals to 2.4. So the total moles we are having 2.9, 2 plus 0.3 plus 0.6, which is nothing but 2.9, and equivalents are nothing but 4 plus 0.9 plus 2.4, which is 7.3. So we can make a table of the different components, and since the moles are given, we can understand and we know the functionality, we can calculate the equivalence, right? So we can see that total acid equivalents are 4, which is in the phthalic anhydride, right? And total OH equivalents, which is in the glycerol and pentaerythritol, which is nothing but 0.9 plus 2.4 from here, which is equals to 3.3. So we can see in differently that acid equivalents are 4, which is from the phthalic anhydride, and the OH equivalents, which is from the glycerol and the pentaerythritol, they are 0.9 plus 2.4, which is 3.3. So now the average functionality, which is FAV, in the non-stoichiometric mixtures, is calculated by this formula, which is FAV, average functionality in the non-stoichiometric mixtures, is equals to 2 into number of equivalents of functional groups of type A, which is N into N 2 into n a naught divided by summation of n I naught, right? So this FAV is equals to this formula. This formula we can apply when there is number of equivalents of the functional group of type A is less than number of the equivalents of the functional groups of type B. So in this we know that uh, we can like the number of the equivalents of the OH is less than the acid equivalents, which is the OH equivalents are 3.3 and the acid equivalents it is 4, right? So the OH equivalents are less and the acid equivalents are higher, which is 4, right? So we can apply the formula mm, formula of uh, the functionality of average functionality in the non-stoichiometric mixtures. Because why it is non-stoichiometric? Because the equivalents are one is lesser and one is higher, right? So number of the equivalents that cannot uh, that can react cannot exceed this. So we are saying that Na naught it is the Na naught it is in the higher amount, right? And Nb naught it is in the, so what is there actually? What it is saying in short is if one of the stoichiometric mixture in one of the equivalent is higher and one of the equivalent is in the lower concentration, so there will be one which is the limiting factor. So limiting if from this we can say OH equivalents are the limiting, which is in the 3.3, which is in the lesser amount. So we can apply this formula directly of the average number of useful equivalents of the functional groups of all kinds per molecules present initially in the reaction mixture, which is nothing but 2 into Na naught summation of the total number equivalents, right? So FAV is equals to nothing but 2 into 3.3. Why we are taking 3.3 here? Because it is in the limiting state, right? And A naught is in the and A naught is always less than and B naught, which is the number of the equivalents which are in the lesser amount is N A naught, which is equals to 3.3 here, which is lesser than the number of acid equivalent, which is in the higher equivalents, which are N B naught here. So we are taking 2 into Na naught, which is the in the limiting amount or the OH equivalents 3.3 divided by 2.9, which is the summation of the total number of the moles, right? So Ni naught is nothing but the summation of the total number of the moles. So we can understand from this what is the value of FAB, which is nothing but it is the average number of the useful equivalents of the functional groups per molecules present initially in the reaction mixture. So we can get this value. From this we can get the extent of the reaction at the critical point, which is 2 divided by FAV equals to 2 divided by this value 2.2759, which is nothing but 0.88. Since OH is in the limiting amount, it is a limiting reactant, its conversion at the gel point will be 0.88. So what we have just done, we have taken what thing is in the limiting amount. So OH is in the limiting amount. So we calculated uh, the extent of the reaction in the limiting where it is limiting. So its conversion we have calculated, which is 0.88. So complete version So complete conversion of OH without gelation is not possible, right? Because OH, if OH will not be there, what acid equivalent will going to do, right? So let's summarize this question, how we approached and how we calculated is, since in this question we need to calculate the, this question asked that can the following recipe, if we mix these things, if we take these the phthalic anhydride, glycerol and the pentaerythritol, if we take all these three, then they will react, right? And the all the conversion, if the complete conversion, like the phthalic anhydride, it is having 2 moles, glycerol is having 0.3 moles, and pentaerythritol, it is having zero point 0.6 moles, right? So these three are having these three modes. If it will react, so will the complete reaction will take place, or like before it will form the gel, or it will not, uh, either it will form gel or it will not form gel. So the question is asking, uh, when it will react, so complete, before the complete reaction, whether the gel will form or not, like it will not form. So how we approached is, so we calculated first uh, the equivalence, because we need to understand there are two things. What is actually happening is, there is this acid base reaction is there, like the acid equivalents are there and the OH equivalents are there. So we need to calculate if what is in the limiting amount. So for that, the phthalic anhydride, we know it is having 2 moles and the functionality is 2. So we calculated the all the acid equivalent as 2 into 2 equals to 4. And in the OH equivalents, which is having, like which is coming from the two sources, glycerol and pentaerythritol. So what we did is we multiply the functionality and the moles of these two, and we get the glycerol as zero point 0.9, like contributing to zero point 0.9 equivalents, and pentaerythritol, it is contributing to 2.4 equivalent. So we saw that 0.9 plus 2.4, which is 3.3. So we are having OH equivalents as 3.3 while the acid equivalent as 4. So the OH equivalent is lesser and the acid equivalent is higher. So limiting one will be the OH equivalents, right? So for calculating the, like first what we are calculating, we are calculating equivalence. So F is representing the useful equivalence of the functional groups of all kind of the molecules, or of the limiting molecule which is present at the zero time in the reaction mixture. So at zero time we are having 3.3 limiting equivalent. So 2 into 3.3 divided by total number of the moles, which is in the total reaction, which is 2.9, right? So we calculated it as 2.2759. And we how we calculate the that the extent of reaction. So extent of reaction is nothing but 2 divided by what is the, at the, like what are the functional groups at the initial point. So which is nothing but 2 divided by 2.2759, which is 0.88. So this, till this much the so till this much the reaction will going to occur. So and uh, 0.88, but we are having more, uh, like we are having more equivalents. So till 0.88 there will be this, after this there will be the gel form. So after 0.88 value, which is the PC value, which is nothing but the critical point of the extent, means after the this value, the 0.88 value, the gel will going to form. So but we are having the more value, so the reaction cannot complete without the gelation. So there will be the formation of gel because the, the critical point is lower value, right? So you understood the solution part, or anyone is having any doubt?
No doubt.
So next question is, in the Flory-Stockmere theory, how is the probability of forming an infinite network or the gel related to the extent of reaction? It decreases as the reaction process, it increases as the reaction progress, it remains constant throughout the reaction, it is independent of the extent of reaction. So we have already discussed the Flory-Stockmere theory in the lecture slides. So how it is in that how is the probability of forming an infinite network relate to the extent of the reaction? Extent of the reaction is nothing but T, right? So how it is related? So the answer is B, as the like it increases as the reaction progresses. So as the reaction, if it will progress, then the probability of forming an infinite gel also increases and the extent of reaction will also increases. So let's discuss what is Flory-Stockmere theory. Just to briefly discuss about it. In that, the gelation process, it like the Stockmere, it discussed about the gelation process during the step growth polymerization due to the cross-linking, and it says that after that the network will form, like the system will transit from the sol to a gel, and it was the first theory which investigated the percolation process, where like the percolation process, which is the special kind of the arrangement of the monomers. And in this theory there are three assumptions, which are all functional groups on a branching unit are equally reactive, all reactions occur between A and B, and then there are no intermolecular reactions. So in the gelation, it only occurs when the branching probability it will be greater than the critical branching coefficient for gel formation, right? And the gel it will form more if the polymer, oh sorry, if the monomer concentration is more, and the reaction, extent of the reaction will be more, right? When will the gel will form? If the monomer is more, or the reactant is more, right? And when the increase in the extent of the reaction, more reaction extent, like the reaction is in wants to proceed in the forward direction. So let's discuss so the probability of forming a network or the gel, like more network or more gel, how it will form when the reaction will be in the forward direction and when the extent of the reaction is more, right? So next question is, what is the critical value of probability for trifunctional branch unit? 1.5, 0.25 and 0.7. So its answer is 0.5. Why? The expression for critical value of probability for trifunctional branch unit is equals to 1 upon f minus 1, which is f equals to functionality of the branching unit, right? And because f, we know that it is given in the question as trifunctional branch, so f is equals to 3. So 1 upon 3 minus 1, which is 1 upon 2, and we can get critical branching coefficient as 0.5, or critical value of probability as 0.5. So option B is correct. So let's move to the next question. Using the mean field model of gelation by Flory and Stockmere for monomer functionality F equals to 3, the characteristic degree of polymerization at an extent of reaction P equals to 0.6 is. So let's solve this question. So it is asking the characteristic degree of polymerization, which is nothing but n star, and its formula is equals to 2 multiply by f minus 1 functionality minus, sorry, f minus 2, which is functionality minus 2, divide by f minus 1, which is functionality minus 1, multiply by relative extent of reaction to the power minus 2. This is our complete formula. So first in this we already know that the monomer functionality F equals to 3. So it is given in the question 2 multiply by F minus 2, which is 3 minus 2. So here divide by F minus 1, which is 3 minus 1. Now we need to calculate this value because this is unknown. Relative extent of reaction, which is nothing but it is equals to P divided by PC minus 1, which is the extent of the reaction, uh, right? Which is nothing but it is equals P is equals to extent of the reaction divided by extent of the reaction at critical point minus 1 is equals to F minus 1, which is the functionality minus 1. Like this we can also write as F minus 1 into P minus 1, which is functionality minus 1 multiplied by extent of the reaction minus 1. So relative extent of the reaction is equals to functionality minus 1, which is 3 minus 1 multiplied by uh, P minus 1, which is P multiplied by P, which is 0.6. It is given in the question as the extent of the reaction P is equals to 0.6, right? So we can put this minus 1. 3 minus 1 is equals to 2 multiplied by 0.6. 0.6, which is 1.2 minus 1, which is 0.2. So we got E as 0.2. So we can put in this formula equals to 0.2 to the power minus 2 here, right? So 2 into 3 minus 2, which is functionality minus 2, which is 1. 2 into 1 is 2. In the numerator it is 2. Functionality minus 1 is equals to 3 minus 1. So it is 2 multiplied by 2.2 to the power minus 2, which is extent of the reaction 0.2 to the power minus 2, which is 0.1 upon 0.2, 1 upon 0.2 uh, to the power 2, which is 1 upon 0.04, right? So when we solve it, we can get 25 as our characteristic degree of polymerization. So you understood the question? Are you following? Any doubt so far?
No doubt.
So let's move to the next question. Using the mean field model of gelation by Flory and Stockmere for monomer functionality F equals to 3, the polydispersity index at an extent of reaction P equals to 0.4. So we need to calculate PDI, polydispersity index value at an extent of the reaction 0.4, where F equals to 3 is given. So what is the polydispersity index? It is nothing but weight average degree of polymerization divided by number average degree of polymerization, right? So we know that average degree of polymer, like this formula is also equals to 1 plus P in the terms of T and F, which is extent of the reaction and the monomer functionality. This formula, the PDI formula, is also equals to 1 plus P which is extent of the 1 plus extent of the reaction multiplied by 1 minus PF, which is extent of the reaction multiplied by monomer functionality, divided by 2 divide, and whole is divide by the denominator is 1 minus P by PC. PC what is PC? PC is the at the critical point. What is the extent of the reaction, right? So in this PDI, which is equals to 1 plus P. P we know it is given in the question as 0.4 extent of the reaction we need to calculate. So 1 plus 0.4, which is 1.4, right? Multiply by 1 minus P F divided by 2, which is 1 minus P given in the question as 0.4. So 1 minus 0.4 into F, which is 3. So multiply by 3 divide by 2. So how we can calculate is 1 minus 0.4 multiply by 3 divided by 2. So 2 we can cancel it by 0.4. So it will give 0.2. So 0.2 into 3 is 0.6, right? So 1 minus 0.6 is 0.4. So 1.4, which is from 1 plus P, sorry, multiply by 0.4, which is 1 minus P, 1 minus P F divided by 2, right? In the denominator, it is 1 minus P by PC. So 1 minus 0.4 divided by PC. So we don't know the PC value, right? Which is at the extent of the reaction at the critical point. So how we can calculate it? Its formula is 1 upon F minus 1. So F we know as 3 given in the question. So 1 upon 3 minus 1 is 2. So 1 upon 2 is 0.5. So we can put here in this equation and we get 1 minus 0.4 divided by 0.5. So which is nothing but 0.2. And when we calculate, we get the polydispersivity index as 2.8. Can we move to the next question?
Yes.
So for a system composed of diethylene glycol, which is having 2 moles, 123 propane tricarboxylic acid 0.6 moles and adipic acid 1 mole. Determine the number average degree of polymerization before gelation. So it is saying we have these things and we need to calculate number average degree of polymerization, but it is before gelation. So let's calculate this question, try to solve this question. So number average degree of polymerization for a condensation polymerization reaction, because diethylene glycol, propane tricarboxylic acid and adipic acid, this is going in the condensation reaction, and in the condensation reaction it will the number average degree of polymerization will be F multiplied by 1 minus rho plus 1 upon R, then plus 2 rho divide by, which is in the denominator is F 1 minus rho minus 2 PA plus 1 upon R whole multiply is multiplying by F plus 2 rho, right? This is the formula already, like in the textbook it's there, and we have from the question that F is equals to 3, because 1 second, yeah, so we have 3 system, right? So we are having this 3 system, and Yeah. So let's let's solve this question. So from this whole formula, we need to see what are the knowns and what are the unknowns, right? Functionality is f equals to 3, right? And then 1 for functionality f equals to 3, we are solving this, right? And then 1 minus rho. Rho is nothing but it is number fraction of all the A groups that belongs to the reactant with F greater than 3. So rho, the formula is, it is actually the number fraction of all the A groups that belongs to the reactant, right? So F, which is the functionality, multiplied by the moles of the F functional AF with functionality greater than 2, divide by 2 into NAA, which is moles of AA, plus F functionality into NAF, which is moles of F functional AF with functionality greater than 2, is equals to functionality is given as 3 into moles NAF, which is given as 0.6, which is the this one, because this structure we are saying that it is of the A R B, right? Which is the hyper branched structure. So we are taking the functionality as 3, and also from this the R, which is the nothing but the in between one, which is nothing but here the propane tricarboxylic acid, which is having 0.6 as the mole. So we are taking NAF is equals to 0.6. So 3, which is functionality, multiplied by 0.6 divided by 2 into NAA, which is the first, which is the NAA, which is the number of the moles of A, which we are taking as adipic acid, which is 1 plus 3 into, which is the functionality into NAF. NAF we have already taken as 0.6, right? So this is the rho value, and from in this formula we also don't know R value, small r value, which is nothing but the ratio of A groups to the B groups, right? Since we know that the diethylene glycol is in the excess amount, which is 2 moles, right? So the limiting will be the adipic acid and the propane tricarboxylic acid in this case, right? And also the ratio of the A groups to the B groups is equals to 2 into NAA moles of AA plus F functionality multiplied by moles of F functional AF with F greater than 2 divided by 2 into moles of BB. So here A is adipic acid, right? So 2 into adipic acid moles, which is 1, plus functionality is 3, and which is AF is this tricarboxylic acid. So 0.6 moles divided by 2 into NBB, which is number of moles in uh, the diethylene glycol, which is 2. So we'll give the value as 0.950. From this, in this equation, now we need to know the extent of the reaction at the gel point, right? Which is here in the equation of number average degree of polymerization, it is written as 2Pa or 2Pc we can write, which is extent of reaction. So functionality, so number average degree of polymerization in this formula, we know F value as 3, 1 minus rho we have calculated already, right? 1 upon R, which is the ratio we have already calculated, plus 2 rho F in denominator, which is divided by F 1 minus rho minus 2 PA. So we just don't know this value, plus 1 upon R plus 2 rho. So we can calculate sorry, PA or PC value equals to 1 upon R plus R rho multiply F minus 2 whole in the square root, right? So we can calculate PC value as 1 upon 0.950 value, which we just now calculated R value as 0.950, then plus R, which is 0.950, multiply by rho value, which is 0.4737, multiply by F minus 2, which is functionality minus 2, 3 minus 2, and whole in the square root. So we can get the value as 0.845. And then next is the next is the we know all the values and we can put into the number average degree of polymerization. So the we can just put the values in the equation 1 and we can get the value as 9.25 as our degree of polymerization. So the average degree of polymerization of the reaction mixture is thus not large at the gel point. So it does not increase rapidly at the gel point. This merely means that at the gel point, many small molecules are still present and it does not preclude the formation of a fractional amount of the indefinitely large structure at or beyond the gel point. So we can say that the number average degree of polymerization is very less. So it will not form a complete gel and there will be some part of the soul will be there. So let's summarize this question. In this question, we need to calculate the number average degree of polymerization, right? So what we did is we know the formula of degree of number average degree of polymerization, which is this, right? In this formula, we uh, we knew already in the equation 1, we already knew that F is equals to 3 because there are three functional groups which are because there are three functional groups which are reacting. So functionality is equals to 3 and then 1 minus rho. So we did not we don't know what is the number fraction. So how we calculated is we calculated it from the below this given formula and then we need to calculate the R value also because the ratio also we doesn't know that in which ratio the group 1 is reacting with group 2. So we calculated R value and then we calculated the extent of the reaction at the gel point from the this formula. So we calculated these three values and we put into the number average degree of polymerization value in formula and we got 9.25 as the value of degree of polymerization, right? So next, so you understood the question?
Yes.
So let's move to the next question. The reaction of phenols with formaldehyde to phenolic resins is very complicated. Assuming for simplicity that in phenol formaldehyde condensation with excess 3:1 formaldehyde, mm, the formaldehyde is in the excess and the phenol is a tri-reactive structural unit and the formaldehyde merely supplies the inter-unit linkage. So calculate the weight average molecular weight of the phenolic resin at 30% conversion of the functional group. So the reaction of the phenol with the formaldehyde. So we have the phenol and formaldehyde. They are reacting and they are forming the phenolic resins, right? And It is saying that in this there is this condensation reaction, phenol formaldehyde condensation with excess 3:1 formaldehyde, right? The phenol is a tri-reactive structural, so 3 is the functionality, and then the phenol merely supplies in the inter-unit linkages, and we need to calculate the weight average molecular weight when there is a 30% conversion. So let's solve this question. So the functionality it is given in the question F equals to 3, right? We know that monomer is this in this reaction. In this case, monomer, first we draw the how the monomer looks like, right? So phenol is there, right? So OH group is there, and in this at second, fourth, and sixth carbon there is CH2OH group, right? So we have we have 6, 7, 8, 9, 9 carbon we are having, 12 hydrogen and 4 oxygen. So we can calculate the monomer molecular weight as 184 gram per mole, right? And we know the functionality as 3. We need to calculate weight average molecular weight, which is nothing but it is 1 plus alpha divided by 1 minus F minus 1 into alpha. Alpha is nothing but extent of the reaction is equals to 0.3, which is given in the question like 30% conversion. So 30 divided by 100 is nothing but extent of the reaction is nothing but 0.3, right? So the weight average degree of polymerization is equals to 1 plus 0.3, which is extent of the reaction, divided by 1 minus functionality, which is 3 minus 1, multiplied by 0.3. So weight average degree of polymerization is 3.25. Now we need to calculate the weight average molecular weight. So how we can calculate is, it is nothing but the multiplication of the weight average degree of polymerization, which is 3.2, multiply by molecular weight, which is 184 of the monomer, minus, why we are taking minus, because there is this one molecule of the water which is eliminating due to the condensation, right? So we are taking the weight average degree of polymerization 3.25 multiplied by functionality, which is 3, multiply by the extent of the reaction 0.3, and then molecular weight 18 of water divided by 2. So we are taking, how we are calculating is weight, like we need to calculate the weight average molecular weight of the resin or the phenolic resin which is formed. So for calculating, we need to multiply the molecular weight into my weight average degree of polymerization. So 3.25 is the degree of polymerization, multiplied by 184 is the molecular weight, but we need to subtract the one water molecule which will be condensed out. So we have taken the this value, which is we calculated this one, and the resin, the polyphenolic resin is having 563 as its weight average molecular weight. So are you following? Let's move to the
Yes,
next
yes.
question. According to the scaling model of gelation, these values are given, and we need to calculate the value of the exponent gamma or in this equation. So scaling model of gelation, in that uh, we need to calculate value of exponent, which is the gamma, right? So from these equations, these two equations in which the characteristic degree of polymerization is related to the relative extent of the reaction is given in the first relation, which is the characteristic degree of polymerization is almost equals to relative extent of reaction to the power minus 1 upon rho, which is critical exponent for 3D percolation in the case of the scaling model, right? And then second equation is given as the weight average degree of polymerization is almost equals to characteristic degree of polymerization to the power 3 minus uh, critical exponent or the Fisher exponent for 3D percolation is almost equals to relative extent of reaction to the power gamma exponent, which is we need to relate this value, this gamma we need to find, right? So in this question, gamma is equals to, like, how we can calculate gamma. The simple formula in the lecture slide, as per the lecture slides, is equals to 3 minus 3 minus tau, which is 2.18, which is also given in the question, its value 2.18, and its value is also constant. This Fisher constant, Fisher exponent's value is constant for the 3D percolation as 2.18 divided by the sigma, which is critical exponent for 3D percolation, right, is equals to 0.45. It is also fixed for a 3D percolation as 0.45. So we can just subtract and divide, and we can get the exponent value as 1.822, right? So let's move to the next question. According to the Flory-Renner equation, what happens to the swelling ratio as the cross-link density increases? Swelling ratio increase, swelling ratio decrease, swelling ratio remains constant, swelling ratio fluctuates randomly. So there is one equation known as the Flory-Renner equation. In that, swelling ratio and cross-linking density, it relates. So how it relates? Anyone? No? When the swelling ratio, it decreases as the cross-linking density increases. So let's discuss why, how it happens. So first, what is the polymer swelling? So absorption of the solvent by the polymer, causing it to increase in its volume. In the case of the polar solvent, typically increases its swelling in the hydrophilic polymers, right? So also, like, uh, in the Flory-Renner equation, it is basically uh, derived based on the balance between the polymer solvent affinity, how the polymer and the solvent, how its affinity is there, and what and their elastic retracting forces are there. Based on that, based on that, the Flory-Renner's equation is there, and the Flory-Renner's equation is nothing but it is given at the bottom as minus ln multiplied by 1 minus phi 2, which is the volume fraction of the polymer in the swollen state. When there is the solvent, it goes into the polymer, it swells. So what is that time? Volume fraction plus volume fraction of the polymer in the swollen state plus Flory-Huggins polymer solvent interaction parameter multiply by the volume fraction of the polymer in the swollen state square is equals to V1, which is the molar volume of the solvent, multiply by N, which is the cross link density, and then whole multiply is phi 2 to the power 1 by 3, which is volume fraction of polymer in the swollen state to the power 1 by 3 minus volume fraction of the polymer in the swollen state divided by 2. This is complete, is the equation, Flory-Renner's equation, or the from which we determine how the swelling happens in the polymer when it goes into the solvent. And at at the equilibrium swelling, the maximum volume of the polymer will be there, which can swell at the given condition, right? So we know now what is the polymer swelling. When the polymer is in the solution and it increases its volume, it's the polymer swelling. And at the equilibrium swelling, it will be the maximum volume or maximum swelling. And these are the equation. This is the equation of the at the bottom, the Flory-Renner equation. So now let's solve the question. So it is saying according to the Flory-Renner equation, what happens to the swelling ratio as the cross-link density increases. So swelling ratio, it will decrease when increasing in the cross-link density. So we can see N is the cross-link density value, right? So N is the cross-link density, and it is inversely proportional to the swelling ratio. Swelling ratio is the volume fraction, right? So it's inversely related as the cross-linking increases, more will be the cross-linking. If we understand physically, more will be the cross-linking, then the swelling ratio will be lesser. So next question is, a network polymer is mixed with a solvent at 300 K, which causes the polymer to swell. At equilibrium, the volume fraction of the polymer in the swollen gel is 0.2. The polymer solvent Flory-Huggins interaction parameter is 0.25, and the molar volume of the solvent is 10 to the power minus 4 meter cube per mole. The number of the active network chain segments per unit volume, which is the uh, cross-link density we need to calculate. So there is this network polymer which is in the some solvent at 300 Kelvin temperature, which causes the polymer to swell. At equilibrium, so at equilibrium, maximum swelling will be there. So at that time, volume fraction is given as 0.2 of the polymer, swollen polymer. And the X chi value in Flory-Huggins interaction parameter is given as 0.25. The molar volume of the solvent is given 10 to the power minus 4 meter cube per mole. We need to calculate the N value, which is nothing but the cross-linking density. So we just now discussed the Flory-Renner equation, and we can just apply this minus ln 1 minus phi 2 plus phi 2 plus chi phi 2 square equals to V1 and phi 2 to the power 1 by 3 minus phi 2 divided by 2. Right? We just discussed this Flory-Renner's equation, and from this we need to calculate N, which is cross-linking density value. N is equals to minus ln 1 minus phi 2. Phi 2 value is given in the question as volume fraction of the polymer in the swollen gel is 0.2. So we can just put plus phi 2, which is 0.2, plus chi, which the value given as 0.25, the polymer solvent Flory-Huggins interaction parameter value we can put, and multiply by 0.2 square, which is volume fraction of the polymer in the swollen gel square, divided by V1, which is the molar volume of the solvent given in the question as 0. Is 10 to the power minus 4, multiply by 5 to the power 1 by 3, which is 0.2 to the power 1 by 3 minus phi 2 divided by 2, which is 0.2 divided by 2. Everything is given. We just need to put the value and need to calculate, and we can get 271.122 mole per meter cube as the number of the active uh, network chain segments per unit or the cross-linking density. So are you following?
Yes.
So next question is, if the number of the monomers in a network strand is doubled, the equilibrium swelling ratio of a network polymer in a theta solvent will increase by a factor of if the number of the monomers in a network strand is doubled. So monomers in a network strand is increasing to double twice. So the equilibrium swelling ratio in that case, which is Q in a theta solvent, how how much it will increase. So in the theta solvent, the equilibrium swelling ratio of a polymer of a network polymer is nothing but Q is directly proportional to n to the power 3 by 8, which is number of the monomers in a network strand to the power 3 by 8. So n is double. So n will become 2n now, which is 2n. So Q1 will be equals to n1 to the power 3 by 8, right? And Q2 will be divided by Q2 is divided by n2 to the power n2 मतलब 2n1, right? 2n1 to the power 3 by 8. So equilibrium ratio will increased. Equilibrium swelling ratio Q will be increased by a factor of, this will cancel, by a factor of 2 to the power 3 by 8 factor, right? So which is nothing but 1 approximately 1.3. Okay. So we are moving to our next question, which is our last question for today. In neoprene rubber vulcanizate containing 90% chloroprene by weight. So there is a neoprene rubber which is in the neoprene rubber in the vulcanized state, which is having 90% of the chloroprene, out of which 1% is just cross-linked, and then chi value is given as 1.13 in the N-hexane solvent. Calculate an estimate of the maximum swelling expressed as volume of the solvent imbibed per unit volume of the vulcanized. So density of the rubber is given and molar volume of N-hexane is given. So let's calculate this question. So molecular weight of the monomer, which is the chloroprene, is can be calculated as its formula is C4H5Cl. So 4 into 12 plus 5 into 1 plus 1 into 35.5 is nothing but 88.5 gram per mole, the molecular weight of the chloroprene. And we are saying that the chloroprene unit 0.01, which is 1% is cross-linked. So 0.01 is cross-linked, which is our E value, right? And then average molecular weight per cross-linked unit we can calculate is as uh, the the molecular weight of the chloroprene monomer divided by its fraction of chloroprene units engaged in the cross-linking, which is 0.01. So 88.5 divided by 0.01 is 8850 gram per mole. So this is the average molecular weight per cross-linked unit. Now we just need to apply the swelling equation, right? Which is the modification of the Flory Renner's equation, which is the neglecting the effect of the chain ends. We can apply this equation, this below equation, which is already discussed in the textbooks. When there is this swelling equilibrium achieves, right? So minus ln 1 minus phi 2 plus phi 2. So phi 2n is nothing but volume fraction of the polymer in the swollen gel at which the activity of the solvent equals to 1, right? Where there is the uh, activity equals to 1, matlab swelling equilibrium has achieved. At that time, what is the volume fraction of the polymer in the swollen state is phi 2m, is expressed as phi 2m. So ln 1 minus phi 2m plus phi 2m plus chi phi 2m square, and whole is in the minus, and then it is equals to V1, which is the molar volume of the solvent, divided by V2, which is the uh, rubber rubber volume or the monomer volume, sorry, the polymer volume, multiplied by the average molecular weight per cross linked unit, which is mc bar, multiplied by this phi 2m to the power 1 by 3 minus phi 2m by 2. It is from the Flory-Renner's equation, the same, right? So when there is the perfect network, and when there is this number average number average molecular weight, it reaches to infinity, means there is the infinite number of the molecules is there in a network. So the weight will, obviously the molecular weight will reach to the infinity. This formula we applies. So in the LHS and the RHS we will compute. So we have already the value of uh, this in the data, the molar volume of n-hexane, which is 131, right? So 131, right, multiply by 1.23, which is nothing but the density of the rubber, because like in the question in the RHS side it is V1, which is the molar volume of the solvent, which is 131.6, divided by the volume of the polymer. So we have density, so 1 upon 1.23, which is here it will come in multiply 1.23 divided by the mc bar value, which is the average molecular weight per cross-linked unit, then multiply by this phi 2m to the power 1 by 3 minus phi 2m by 2, which is same in the as per the question, or as per, sorry, as per the formula for Flory-Renner's formula, it is the same. So 1.131.6 multiply 1.23 divided by 8850 will be nothing but 0.0183, and multiply by this phi equation. And then LHS side, only chi value is given, which is as 1.13. So we can just in the LHS equation. So we know both the LHS and RHS, and now we can compute the phi 2m value from the like graph we can get, and this graph at the bottom we have plotted between phi 2m, which is the volume fraction values, and how the like how the functionality f is changing with respect to the phi 2m. And in this equation when we solve it, there, like from this plot, we at the interaction point, this phi 2m, which is at the equilibrium, swelling equilibrium, we get 0.757, right? So maximum swelling will be 1 minus phi 2m divided by phi 2m, which is 1 minus 0.757 divided by 0.757, which is nothing but 0.3 volume per volume, and the polymer will swell to 1 upon 0.757 or 1.3 times of its original volume. So you understood this question? What we have just done, we just did, we have the Flory-Renner's equation, which is at the swelling equilibrium, we have this equation. So what we did is, in the chi value, we just in the LHS part we put the chi value as 1.13, we know the V1 value, which is the molar volume of the solvent. We know the the density of the rubber, and we calculate the its volume from that, and then the average molecular weight per cross-link unit we calculate from its the chloroprene monomer molecular weight divided by how much the fraction of the units which are getting cross-linked, which is 0.01. So we from that we calculated the average molecular weight of the cross-linked units, and these values we, and this is the formula, and this is unknown. So from this formula only the phi 2 m value is unknown, which is the volume fraction of the polymer in the saline state. So we what we did is we just plotted the value, right? Because we know this phi 2 m, that from this curve, if this is crossing, if it is intersecting this value, it is matlab, because it is at the swelling equilibrium value. So phi 2 m value, which is at the swelling equilibrium value, we just calculate from the graph, and we understood that the maximum swelling will be at 0.3 volume per volume, or how much is the polymer swollen. Polymer is swollen to 1.32 times from the original value. So you are following the lecture. Uh, are you solving this question?
Yes.
So today we have discussed about the branching hyperbranched polymers, and we calculated the number average degree of polymerization and the weight average degree of polymerization. Then we discussed about the dendrimers, and we discussed about hyperbranched and the gelation on the network, how network polymers. And then we discussed about the mean field model of gelation and the scaling model of gelation and the Flory-Renner's equation. We discussed some of the problems based on that. And in the next class, we will be discussing about the crystalline polymer phase, amorphous polymer phase, and the mechanical properties of the polymers. And please go through the 3 lecture videos for the next class. This is the YouTube channel link, and where I'll be posting the recorded video, and then the Google Drive link where I will be uploading these lecture slides. My email ID is shikha.s.cl@iitg.ac.in. Thank you so much for joining the class. And next Sunday, 4 to 6, we will be discussing our next class, which is the week 6 lectures. So thank you so much.